Hello and welcome to this section of modeling chemical datasets. I'll be focusing on the predictive chemical modeling based on the regression-based methods. The predictive models have become a common part of modern-day drug discovery. Models are used to predict a range of key parameters, including like physical properties of target activities such as the CYP or the hERG inhibition, like binding geometry and affinity of small molecules into protein targets. So the basic aim of this presentation is to give an idea of what are the pitfalls and how would you go or move on in doing chemical predictive modeling, and what are the major factors you need to consider while making a predictive model. So the major questions you need to ask about: how does the dynamic range of the data being modeled impact the apparent performance of the model? The dynamic range comes into play with the activity values, like for example the IC50 values, and how would you select the IC50 values or the activity values to make a classification models. What are the pitfalls of using activity values to make a classification model, and also how does the experimental error impact the apparent predictivity of a model, and how we can determine whether a model is applicable to a new data set, and also how should we compare the performance of the regression models. So you can see you can check the um, there's a good chapter which was this whole presentation is based on from a book which was edited by Jagan Bejurath, and most probably it will be available to on the IU coming week. So you can access the book named Cheminformatics on Drug Discovery, and you can see this chapter. I've put the link out here and you can access it. So this presentation is based on that first chapter, and they have actually give a lot of uh, interesting ideas, and also explain factors how to design a predictive model, and also the all the codes are available, so you can just play with those codes, and it's just it's just like the reproducibility, so that the one can use the codes to reproduce the same data. So that's why the codes are all been given, and you can use those codes in other experiments. So in this example, we'll be focusing on the aqueous solubility, the solubility in aqueous solubility of the drugs or chemicals, and try to build and evaluate a predictive model. The solubility in water buffer is kind of very important parameter in drug discovery. Poorly soluble compounds tends to have poor pharmacokinetics and can precipitate or cause problems in assays. The prediction of aqueous solubility has been an area of very high interest in pharmaceutical industry, and over like 15 or 20 years there's been a lot of papers on this domain. The challenge in developing a solubility model is that lack of solubility of a compound can vary depending on the number of factors, like the temperature at which the solubility measurement is taken, and also the purity of the compound and the crystal form of the compound, which can exist in different polymorphs, and which can vastly differ in the insolubilities. So for modeling, we have taken like three data sets: the Huskonen dataset, the JCIM dataset, and the PubChem dataset. Huskonen dataset consists of 12 12 experimental solubility values, that's the log S values, and the data is extracted from the AquaSol database from the Yalowski group, and the other one is the JCIM consists of 94 experimental solubility values that were published in a kind of blind challenge in 2008. And another one is the PubChem data set, which is a subset of like 58,000 data set. That's most probably the AID 1996 in the PubChem bioassay data, and they've created a subset of 1,000 values to for this exercise. So we begin by formatting all the data as log s, and which is kind of important because that's a standard we need to follow. The log of molar solubility of the compounds and data. So data in the JCIM and the PubChem were transformed into log s using this equation, and so that all the data has been kind of normalized in terms of log s. So it's pretty easy to model. Uh, Coming to the datasets, when we plotted the box plots of the different datasets, that's the Huskonen dataset, the JCIM, and the PubChem, we can see that the Huskonen dataset spans more than 9 logs, while the JCIM spans 5 logs, and the PubChem spans much smaller than like 2.4, 2.5 logs. On measured solubility in drug discovery programs typically range between like 1 to 100 micromolars, that is log s is between -6 to -4. So now here we can consider the PubChem dataset is a more representative dataset that is commonly encountered in drug discovery than the other two datasets. So remember, the PubChem is considered the representative datasets. So the requirements of to build a classification or to build a predictive model, we need a reliable experimental data. You can find a lot of like data sets, primary screening, secondary screening. I think working with the secondary screening data is really useful rather than the primary screening data, so that makes your model much more reliable. Other than that, you need a very good set of descriptors. There are a variety of chemical descriptors available. Some of them are open, some of the descriptors are openly, some are commercialized. For example, the CDK, the RDKit offers a lot of very good descriptors. So in this task, the author have actually used the RDKit 2D pharmacophore descriptors to build the predictive model. And also you need a very good machine learning method to make a very good predictive model which can overcome the like overfitting, and does not you know yeah. So coming to the classification model, there are two types of model you can build. The first one is the classification model. The classification model determines the membership of an object in a group or category. So, in case of aqueous solubility, you might attempt to classify molecules as soluble or insoluble based on the predetermined cutoff of, say, 100 micromolar. So we would classify all the molecules with the solubility greater than or equal 100 micromolar as soluble, and all molecules with solubility less than 100 micromolar as insoluble. So taking these cutoff points is a real is part it's very challenging. There exists edge effects. So for example, like on a value of 99 micromolar will be considered insoluble, while a value of 101 will be considered soluble. So it's very tough to use this classification model to to build like insoluble and soluble data. Uh, so and also for a scientist on drug discovery, so they like to use a predictive model to design new compounds with improved properties. While a classification might be useful in designing a soluble compound from an insoluble compound, it will not allow you to improve the solubility of an already soluble compound. Talking about the regression model. The regression model attempts to predict a real value based on the existing data and a set of molecular descriptors. So it can be quite useful as a part of optimization, and it's often difficult to create a regression model with a limited dynamic range. It's very difficult. So many of the ADMET assays like the HERG and the CIP typically report data on a kind of 2 log range, and sometimes the model doesn't it's due to the unreliability limited dynamic range, the model becomes very unreliable. However, in this exercise we'll be using regression, random forest regression based model to find out what kind of error might arise in doing a predictive model. Coming with the evaluation of a predictive model, so we normally use Pearson's R, the Kendall Tau, and the RMSD, but the considering like no, the Pearsons are, it's kind of the correlation coefficient, or the square of it, and the value can range between -1 and 1, and 1 with a value of 1 indicate a perfect linear correlation, -1 being shows inverse linear correlation, and 0 indicating absence of correlation. The dynamic range of data can the dynamic range of the data uh, can bring a dramatic effect on the Pearson R. And also we don't there's some problems with using Pearson's R, so that's why we use some non-parametric measures, also the Kendall Tau. So Pearson R is very sensitive to outliers and all, and to the distribution of the underlying data. So that's why employing a rank order of values, it's considered insensitive, and actually it gives you the perfect more perfect score, or you can say a perfect metric to evaluate a model. Apart from that, we also use the root mean square deviation. That's considered the paired values of the x and the y. RMSD can be calculated using this equation given below. Okay, the steps involved in building a predictive model, like, so first we need to integrate the experimental data and the molecular descriptors, then divide the data into training and the test set, then build a predictive model from the training set, and then use the model to predict the test set. So here's the random forest model. uh, The random forest model, though, we have actually two data sets here. The data sets, the full data, we actually use a 70% training set and 30% test set. So the first is the training set of 891 compounds, and a test set of like 383, and a Pearson correlation comes out like 0.95, and Kendall Tau is 0.81, and the RMS error is 0.64. And this model was quite similar to the performance which the literature reported. And also we created a subset of from this model, like containing 303 from the full Husk-Connon data set, like containing 303 compounds in the training set, and a test set of of 130. Now, earlier we have said like the Husk-Connon dataset spans a wide range of solubility values, as we have seen in the box plots. The range observed in the dataset is much larger, and that is why typically seen in drug discovery projects. So if we reduce this dataset only to those log S solubility to -6 and to minus, so collect only the compounds within range of -6 and 0.3, which is a kind of more typical. So in that case, the Pearson correlation drops, even the Kendall Tau, and also the RMS error. So we can see here that the dynamic range in the dataset can have a large impact on the apparent like correlation between the experimental and the predicted activity. Literature replete with examples of what appear to be impressive correlations on datasets that span an unrealistically high range. And the authors who generate predictive models for protein ligand often use datasets that spans like 12 orders of magnitude. The reality in is that the binding affinity of compounds typically encountered in drug discovery is normal, like 5 to 6 orders of magnitude. So when building a predictive model, one should consider the dynamic range of the data used to build the model, and how this range compares with the range of the data to be predicted. So there are also some experimental error about and the model performance. So experimental data points, what the scores what we have, the solubility has always an error associated with it. The log S of a compound if suppose is -6 and data point has an error almost say about zero point 0.3 or 0.25 log units, the actual value should be in range between -6.3 and -5.7. So Brown and some co-workers actually studied the relationship between the experimental error and the model performance. They carried out like theory series of theoretical experiments where Gaussian distributed random values were added to the data to simulate the errors. Others calculated correlation between the measured values and the same values with the simulated error, and the correlation can be thought of as the maximum correlation possible given the error in the measurement. So the table shows the maximum possible correlation for each of the three solubility data sets. If data sets we have been examining and what they have examined, where the experimental errors are considered like zero point 0.3, zero point 0.5, and 1 log. Note that the error has more of an impact on a dataset like PubChem, which has a limited dynamic range. So in the experiment, the error zero point 0.5 log, then the best R square achieved is 0.60. And note that the error is 1 log, almost half the dynamic range of the dataset. It is impossible to obtain a meaningful correlation. Because the dynamic range of the Huskonen dataset is large, the impact of error on the correlation is much less significant. So when building any sort of predictive model, it is important to carry out the type of analysis outlined here, like adding the experimental error. Uh, So another thing is we need to consider is the model applicability. Formals often perform very poorly on molecules that bear little resemblance to those of the training set. For example, when we did a Tanimoto similarity of the test set of the Huskonen set and the JCIM with the training sets. So we actually use the training set of molecules from the Huskonen and then use the Huskonen test set, the JCIM set, and the PubChem set to perform the similarity between the data sets. We found like the mean similarity of Huskonen was 0.76, the JCIM 0.74, and the PubChem is quite low. So and the similarity fingerprints used is the 2D pharmacophore, which is implemented in the RT-Kit library. The Huskonen set is similar to the training set, and the median similarity is also is like 0.78. So one would assume from that, from the Huskonen test set, that approximately half of the molecules in the Huskonen test set are similar to the molecules in the training set. We would expect the performance of the model of the data set should be reasonably good. Also, taking the JCIM is less similar to the training set. The median is like 0.62 and the mean is 0.74. The box plot and the higher mean indicate that there are a number of compounds in this set that are similar to the training set. The absence of whiskers in the box plot uh, indicate uh, mm, uh, indicate that the similarities are more narrowly distributed. So we would expect a moderate performance from this data set. And taking the PubChem data set, it's very different from the training set. The mean and the median similarities are it's very low. Similarities in this range are what we would tend to expect from the pair of random like compounds. We would expect extremely poor performance for this data set. Also, below is another table which shows the R square, Kendall tau, and RMS error for the prediction of each of the three data sets. As was earlier predicted earlier, the Huskonen test set gives a reasonably good prediction with R square 0.92, 0.92 RMS error of 0.58, and the JCIM can be considered moderate, and the PubChem like it's not quite good at all, very high RMS error. So when evaluating potential performance of a model on a new set, it is important to perform this type of analysis whether one can expect useful prediction to come from a model. This is particularly important when working with like you are working with collaborators and have limited understanding of computational models. So coming to comparing predictive models, when comparing predictive model, comparing correlation coefficient, we must not only consider the value of the correlation coefficient, but also the confidence interval around the correlation coefficient. And if for example, which is given in the table below, if the confidence, if the two correlation if they overlap, so what we did, uh, we took a subset of the Huskisson set of 25 compounds, 50 compounds, and 100 compounds, and used two different methods like random forest and some other method, which is given as method A and method B, and compute the R and the confidence interval. So coming from this table, we found that if two of the correlations, if the confidence interval of the correlations overlap, we cannot claim that one predictive model is superior to another. For example, like 0.60 and 0.91, and like, and then the 0.84 and 0.97. So the 0.84, this method AP for subset 25, kind of they overlap with the method A. So we cannot claim where this model performs better than the other. For a subset of 50 compounds, we can see there's a small difference of like 0.01 mm, for the 95% confidence interval. So but still we cannot tell whether this one is superior to another. And for a subset of 100 compounds, we find there's a clear separation between the confidence interval, which implies there is a clear separation between correlation coefficient, and we can we can say there is a like method B performs better than method A for subset of 100 compounds. And all this code and everything is available at this site, so you can go and just see and download the code and run.